So in order to give you these lectures, so these lectures are somehow intended to explore the BRST symmetry more from the field theory point of view. Last week, together with Nathan Berkowitz, you have seen the application of BRST symmetry to superparticle, particle, strings, superstrings. But I don't know how many of you have seen BRST symmetry and in the context of gauge theories. And also Nathan Berkowitz last week actually introduced this concept of antifields. But the antifields actually have an historical reason why they are called antifields, why they have been introduced in the literature. And so I will try to give you somehow an overview of this, so please ask questions, and then next lectures I will give you a simple model, which actually is very useful because then you can somehow going from gauge theories to more to superstrings, and then you can probably understand even better what actually Berkowitz was doing last week. So first of all, I will start for a very simple example, which is just a Maxwell theory. Maxwell theory, and so you know that Maxwell theory is characterized by the fact that you have a gauge potential, a mu, which is a field. Okay, I will not use very geometrical technique, but just use a field theory technique. So field theory notations and field theory techniques. So I will rather not be very geometrical. Anyway, BRST symmetry has also a deep geometrical meaning, and so if you like, I can give you the reference if you are interested into that. And there is, of course, a interesting interplay between BRST symmetry and differential geometry, and in particular the differential operators in differential geometry, namely the exterior derivative in differential geometry. In some cases, can actually be understood as really the BRST operators for quantum field theory. But I will use quantum field theory notations. Okay. So once you have this object, the gauge potential, you define the field strength, the Maxwell tensor, as d mu a nu minus d nu a mu. Okay, and we know that why you define this quantity. Actually, this quantity has the property that is gauge invariant. Gauge invariant, and the gauge invariance under the following symmetry, namely the variation of the gauge potential is just a derivative of some gauge parameters. So this lambda x is not the Q spinor of Nathan last week. It's just a function of the coordinates. Is a commuting quantity. Okay, is a commuting quantity, and this is just a gauge transformation. Now we know that under these gauge transformations, the field strength it is invariant. Okay, so it is gauge invariant. And so therefore, the first steps is to construct, well, this was done by Maxwell, to construct an action, Maxwell action, which is minus 1/4 f mu nu. And we know that this action, well, it has been built in a disk covariant way in order to, let's say, to contains both the electric and magnetic fields. We know that this has the correct structures, and we know that this action has the gauge invariance. Okay, the gauge invariance is not something that, say, is an auxiliary. It's a crucial, because actually, if you look at these actions, which describe, let's say, which describe the theory in terms of a potential which has 4 degrees of freedom, because let's say this has 4 degrees of freedom. I'm just counting 1 degrees of freedom as one field. So there are 4 degrees of freedom for this quantity here. But this action, it being gauge invariant, is not describing 4 propagating degrees of freedom, but actually only 2 propagated degrees of freedoms, which are exactly the 2 polarization of the photon. Okay, namely, the fact that you want to write that you like to write down an action which is Lorentz invariant, okay, which are all the group properties, Hermitian, Lorentz invariant, and is real, so all these good properties, then you need a potential which has 4 degrees of freedom. So it must be a 4 vector. But then, in order that this quantity describes really 2 propagated degrees of freedom, you need the gauge symmetry. So the gauge symmetry is a way to write down something in a covariant way with the correct counting of degrees of freedoms. Okay, this is a crucial point. But then, when you do gauge fixing, so when you want to write down somehow the quantum version of the theory, you need a way to recover that this theory must describe only 2 degrees of freedom and not 4 degrees of freedoms. So I will try to convey these issues in these lectures. Okay. Now, of course, this is not the only gauge invariant operator that you can build. For example, you can build, the energy momentum tensor. In this case, there's something like f nu rho minus 1/4 of eta mu rho eta mu nu f square. Okay, this is another gauge invariant operator. Of course, then you can build a whole list of gauge invariant operators. Gauge invariant operators, which are built in terms of f mu nu and all possible derivatives, rho, sigma, alpha, of f mu nu. So written in terms of this quantity, which is gauge invariant, and all derivatives. Now here I wrote down as a covariant derivative. In this case, we are talking about only Maxwell. We have only, let's say, ordinary derivative. Let me write down in this way. Okay, for Yang Mills you have covariant derivatives. So you can build gauge invariant operators written in terms of these ingredients. And of course you have a big list of these gauge invariant operators. Namely, so you can characterize completely the theory in terms of the Lagrangian gauge invariant operators. And so at the end of the day, when I fix the BRST, so when I construct the BRST symmetry, I want to recover the same information. So I want to understand where are the gauge invariant operators. Also, how can I build gauge invariant operators starting from a BRST symmetry? Now, of course, this theory has some problems. Okay, if you want to quantize it at classical level, we know perfectly how it works. We know the equation of motions. Equation of motion f mu nu equal to 0. Now here, of course, I'm talking about a free Maxwell theory. If you want to add a current, so you need to add some current, so you modify accordingly the Maxwell equation in this way, and then you know that this current, in order to satisfy this equation, satisfy also some consistency conditions, which is just a conservation of this current. Okay. I'm not going to describe coupling with matter, but just only to describe only the gauge part of the theory. Okay. Unfortunately, when you try to quantize this theory, okay, so you try to quantize this theory, you run into some problems. So, quantizations. Okay. So there are actually 2 ways to quantize the theory. Well, there are several ways to quantize the theory. Let's say the main way to do it is by choosing, for example, an Hamiltonian approach. An Hamiltonian approach of the quantization. Hamiltonians means the following: you have to construct the conjugate momenta of the fields. So you define what are the fields and what are the conjugate momenta. However, when you construct the Hamiltonian approach, you immediately you break manifest Lorentz invariance. So therefore, you can do it. Okay. For example, if you want to see how Hamiltonian approach is developed, for example, you can check this book, Itzigson Zuber. there is a section about quantization for constrained systems. It is very, I think the title of the book is Quantum Field Theory. So this is a kind of very well-known books. And in these books, there is a section about constraints systems where you can read the Hamiltonian quantization for Maxwell for electrodynamics, if you want to understand this way. However, I don't want to break Lorentz invariance, okay? So therefore, I choose a different path. So I want to try to do a path integral approach, okay, which is more related to Lagrangian approach. Okay, so I'll try to stay as covariant as possible. Okay. So then you do the following. You say, well, let's try to construct a path integral. Okay, let's try to construct a path integral. Okay, and to do that, you follow the usual path. Okay, the path integral for the gauge fields is just you integrate on some measure. So you needed to define what is the measure on this configuration space, which is of course is a big space. You need to define this measure, but then the way is to write down this action. The action is a function of the fields, and the action is just the integral, the four-dimensional integral of the Lagrangian, the Maxwell Lagrangian. Okay, so you define the path integral in this way. Okay, however, this definition is completely ill-defined. Okay, for several reasons. Okay, one of the reasons is the following. Okay, now since this action it is gauge invariant. Okay, so there are directions. Of course, there are directions where you integrate along these directions, but there is no dependence on that direction in this action. So the integral, essentially this measure could in principle be split in two pieces. One piece which is called, let's say, gauge orbits, and one piece which is some orthogonal to the gauge orbits. Okay, the orthogonal of gauge orbits gives you something which is a well-defined integral. Well, besides the fact that you need other type of regularizations, but when you start to integrate on the gauge orbit, since this action does not depend on this gauge orbit, that automatically gives you something which is an infinite volume. Okay. Of course, you can say, well, maybe I can divide this quantity by this infinity volume, okay? But you have to regularize anyway, so you have to do something to really to split the measure in this way. But the splitting of the measure in this way is also affected by the fact that if you really want to do it, you have to do it in a non-Lorentz invariant way, okay? So this is one of the problems. Let's say the splitting can be done, or let's say can be somehow taken under control. For example, if you put this path integral on the lattice, okay, somehow on the lattice you can do it a kind of a splitting in this way of the measure and start to integrate it on some gauge invariant combination. But you have to rephrase your action in terms of a plaquette type of path integrals. Okay, good. Okay, so this is one of the problem. Okay, however, I would like to show you other way to see the same type of problem emerging in a different way. Because of course, this is a four-dimensional theory, so you know that when you consider quantum field theory for four-dimensional theories, you run into some problems when you try to multiply the fields. So in interacting theory has some problem because you have to take into account divergences coming from, let's say, Phiman diagrams calculation. But we are not going to discuss renormalization at this point. Okay. Now you can say, well, okay, I want to somehow to find a convergent way to do this integral, okay, on this gauge orbit. And one way to do is, okay, let's try to add here somehow a convergence in factors. So add into the theory some things in order to make it somehow a convergent integral. Eventually, I will remove this regulator. I will remove these additional pieces in such a way that my result will be independent of the regularization. So let's say the trivial thing to do here is somehow to add to the theory something, a new terms. Let me write down this as a gauge fixing, which will depend on the fields. Okay, I will write down the action is just the integral of the Lagrangian. Okay, so I'll try to add a piece. okay, to the action in such a way that this integral is convergent, okay, but excuse me, add a piece in such a way that this integral is convergent, but of course I'm going to modify the theory, okay, so I adding a piece, okay. Of course the best thing is to add in something which does not affect the final result, but then I have to do it in a clever way, okay, and then I will tell you how to do it in a clever way. Suppose that you do this, so you add the gauge fixings. So if you add the gauge fixings, and then let's consider again the Lagrangian here, okay. So if I write down the Lagrangian, or even better, if I write down the action, okay, if I write down the action, which is just d for x of minus 1/4 of m mu nu f mu nu, okay, I can rewrite this action in this way. I just do a partial integrations. So this is just d mu a nu minus d mu a mu squared. If I do partial integration, I get a minus, so plus 1/2 integral of d for x, okay? And then when you do partial integration, this can be written in this way: a mu box a mu minus d dot square, in this way, okay? So I get this answer here, where this is just the box, okay, and this is just the square of the divergences of these fields, okay. Now, we know that this combination with the minus sign in the between is just the right combination, which allows us to have really gauge invariant action, okay? So these two terms both contributes, and then therefore they cancel when I perform a gauge transformation. Okay, so therefore, if I eliminate this one, these terms, okay, by adding to the theory exactly the terms which cancel this one, okay, I end up with something which is just a mu quadratic with a box, okay. So that would be a reasonable theory, because this looks like a theory for scalar fields. For scalar fields, we have like 5 box phi, and we know that in terms of this theory, we can build up our Phiman diagrams and perform the quantizations, okay? Suppose that, therefore, I eliminated these terms, okay, by adding a gauge fixing terms, okay, and I end up with this action here, okay? Now you start doing quantizations, okay? Starting doing quantization means what? Well, you can do it in 2 ways, but let's say let's do it in the simplest way. One way to do it is, first of all, you compute the conjugate moment of a mu, okay, and then you define your you find the bracket, okay, in order to quantize the field in this way, okay. So you find out like a mu dot of x and t. So this is just the spatial component of the coordinate. Commutator with a nu of y times t. So this is just the commutator at the same time, okay, equal to I over h eta mu nu delta x minus y. Okay, so these are the quantization rules that you set up to quantize this theory. I just rephrase what you are used to do it for scalar field theory. Just for one scalar field theory, you construct such commutation relations between the fields at the same time. So those fields are put at the same time, but at different space-time points. And on the other side, you get I, H. Here there is the metric eta mu nu. Okay, and then there is the delta cube for the space-time, okay. So this is just the commutation relation between the fields given the space-time. So the usual quantization, canonical rule for the quantizations, okay. But you see what happened here, okay. Here on the right-hand side, it appears exactly the eta mu nu, right, okay. Now, of course, it depends which kind of metric I'm going to consider, okay? If I consider, for example, in Euclidean space, okay, well, this object is, well, definite positive or definite negative, okay? But if you consider like a Minkowski space, so really quantizing the Minkowski space, this matrix here is not neither definitely positive. So it has a 1, minus, 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 or if you like, minus 1, 1, 1, 1. So this object is not definitely positive, okay? And so what happens? If this object is not definitely positive, okay, this means the following, that when you build your states, when you build your states. And how you build the states? Well, you define a vacuum, okay, and then you build the states just acting by some, let's say, creation operator obtained by quantizing these fields. And then when this creation operator, okay, some modes of this creation operator acting on this vacuum, you create a state, let's say, with one photon, okay. However, the trouble is this point, the Hilbert space built out of those states has no norm, okay, has a scalar product, but is not definitely positive, okay. So therefore the Hilbert space obtained by this, the Hilbert space, has no really definite norm. So it's not really any Hilbert space in a good sense. So therefore, I cannot define really a good quantum field theory in this framework. Okay? So that's the main issues. So therefore, when you quantize in this way, by starting by using the gauge fixing, okay. So one of the problems is that, well, I do it by hand, so I just cancel these terms, I remove this by hand. Suppose that I find out a way to do it in a, let's say, in a non-dangerous way, but suppose that I'm doing that. It turns out that the quantization of this model, okay, is a sick, because actually there is no really definite positive norms to define your physical states. That's one of the problem. Okay. So then, how can I avoid this issue? So how can I solve this problem? So how can I define a Hilbert space where actually you have really physical interpretations, where you're really doing quantum mechanics? By the way, I can tell you, okay. These issues, for example, this issue of defining a correct physical states, okay, it is the same problem that you find in string theory. Last week, Nathan Berkowitz was mentioning about the quantization of superparticle, for example. When you quantize superparticle, I mean, just a side remark here, you have some coordinates, he called it xm, and then associated to that, there are also some momenta, pm, all right? Now, in the action, when you write down the action for the superparticle, I just repeating what Nathan was doing last week, okay? Because in order to compare the two situations, so what happened for string theory, superparticle, and in quantum field theory, so you have the following action: x dot m plus e over 2, okay? And here there is a p square, okay? Now, to define the p square, you need another ingredient, because this p square, it is just the pm Pn eta mn, okay? So you need a metric, in this case it's just the metric in the target space, which is not definitely positive. Suppose that you work in 10 dimensions, this metric has 1 minus the identity on the 9 directions, like this. So if you work in a Minkowski space for superstrings or for particle or for superparticle or for bosonic strings, you need this metric on the target space, okay? I just stick to 10 dimensions, but you can do it also for 26 dimensions for the bosonic strings, okay? But suppose that the metric that you introduce is a Minkowski type, like 1 plus and 9 minus on the diagonal line of this diagonal matrix. It turns out the following: that when you quantize this model, the quantization rule is the following: pm xn is equal to I over h eta mn. Okay? Do you remember? This was the equation that Nathan was writing last week, okay, which was the quantization rule for the particle. However, you see the same problem here. When you create states acting with this operator, now is an operator on some Hilbert space, you run into the same problem, okay, because here there is the metric which is not definitely positive. So this is the reason why you need a gauge invariance of this action in order to find a physical state. So the BRST symmetry that Nathan was constructing last week was indeed in order to solve this issue. Otherwise, you don't have a physical space which has the correct physical metric where you can define correctly a norm of the quantum theory. Okay, so the same issue that you find for super Maxwell, you find for the particle, you find for the let's say you find for bosonic strings, and then you find for the superparticle, and you find for the superstrings. Okay. will show you, I mean, I'll just repeat what Nathan was doing last week in order to, let's say, to compare the two, the two framework. Okay? Okay, so how can I solve these issues? Okay, how can I solve these issues? The idea, so remember, I have two problems. One, the problem is the quantization rules, and the second problem, I want to add something to the theory in order not to change the theory, okay, but to add something which is somehow harmless to the theory. And also I want to reproduce not only the Hilbert space, but I also want to reproduce the full set of gauge invariant operators that I have in the theory. Okay, so I have this goal. Okay. Before going on, I want to show you one other ingredient, which is the following. Now, when you write down the things at the quantum level, okay, of course there are different ways to work. You can work on computational relations. You can work with the path integrals. Okay, there is another way to do it, which is also very convenient, is to work what is known as gamma of mu, which is also called effective action. Effective action. There are two ways to define this effective action. One way is to define it from the path integral directly, or you define in terms of Phiman diagrams, okay? So this one particle reducible Phiman diagrams, which allow to define this quantity here. And they are related, okay? So again, if you want to find some reference for this construction, you can see in this Zuber book or other quantum field theory book, like, well, I don't know, maybe, well, any quantum field theory book, there is the definition of effective actions, okay? Let's say the effective action reduced to the tree level to the action, okay? But it contains also the radiative corrections to the theory. Now, in terms of effective action, what I can write down what is known as the symmetry at the quantum level, which is just word identities. I will do it because actually the word identities are just the manifestation at the level of path integral of the gamma or the effective actions of the gauge invariance. So it's a way to rephrase the gauge symmetry of the fields of the theory in terms of some identities among Green's functions. You know that when you quantize the theory, you don't see the fields, okay? What you see are correlation functions. This is just your ingredients. You're not really computing the fields. If fields has no physical meaning, what you're computing are correlation functions. Correlation function between fields in some cases, or between gauge invariant operator. And those are the physical quantity that you can really measure in quantum field theory. So therefore, the symmetry, namely the gauge symmetry, is just a manifestation that among those correlation functions you have relations, okay? Of course you have an infinite number of those relations, and this infinite number of relations are rephrased in terms of word identities. In the case of Maxwell theory, the word identity can be easily written this way. Now we know that the action or the effective action must be invariant under such a symmetry, okay? Now I can rewrite this in this way. So now here I have only one field, which is just the gauge field. So I can rewrite this variation of the action. I will call it just an effective action or a quantum action, or for short, I will call it an action, okay? In such a way that the variation of this action can be written in this way, just using the chain rule, is this for d for x, d of a mu of x, and here there's a functional derivative of this object here, respect to x. You see, this object here is just a functional of the gauge fields or other fields of your theory, and then this is just a functional derivative of this with respect to those fields, okay? And then this is just the chain rule, okay? So you're just performing a variation of this action just by changing the fields on which this action depends on, okay? Now let me write down this variation here, which is just d for x, d mu of lambda of d gamma of a mu x, okay? Then I do partial integration, so I just do a partial integrations, x lambda of d mu of d gamma of a mu, okay? And of course, this equation must be true for any gauge parameters, okay? This equation must be true for any gauge parameter. So this means that this equation must be valid also locally. Locally means what? Means locally means that I need an equation which is d mu of d gamma of a mu, okay, must be equal to 0, okay. Those are the word identities for just for free Maxwell, okay. So this means that any function, for example, if I want to consider a correlation functions for two gauge fields, okay, for two gauge fields, so I have to take two functional derivatives respect to a mu x and respect to a nu y, okay. This I will call it as a 2-point functions, mu nu x and y, okay. So this and just then you take a derivative and compute it for a is equal to 0, okay. So this is just the definition of 2-point functions. If you need a 3-point function, you just take a 3 derivatives, 3 function derivative, and then you set a equal to 0, and you create a 3-point function, 4-point function, anything. Let's say at the quantum level, those are defined as the correlators for one particle irreducible diagrams, okay? So you can connect them to the path integral version of it, okay? But this is, let's say, in quantum field theory book, you can do this step, but here I don't need that, okay? Now you see that if I take one functional derivative with respect to a of these equations, okay, so I get what? I get a d mu, derivatives of gamma of a mu dA nu must be equal to 0. Just put a equal to 0. So this means that I get minus d mu of gamma mu nu of x and y must be equal to 0. Okay. So this means what? Means that 2-point functions, a 2-point function, so the correlation function, one particle reducible correlation functions of two Maxwell fields must be divergence-less. Or, if you like, in the momentum space, if you go to the momentum space, this tells you that these 2-point functions in the momentum space, which depends only one single momenta, must be transverse. These are the usual word identity, which tells you that the 2-point functions for two Maxwell fields is indeed the transverse function. So, contrasted with the momentum p, this must be equal to 0. Okay. Now, in the case of a free Maxwell theory, all the Green's function or n-point function satisfy an equation like this. Now, I will show you that what happened for Yang-Mills, and then actually you will see why I did this derivation, because we will do it for non-abelian ones, but then I will recover the word identities for non-abelian gauge symmetry, but then I will recover the word identity for the BRST symmetry, and you find out that for the BRST symmetry, you need one additional ingredient, which actually motivates the introduction of these antifields. So the antifields were born because of trying to write down the word identity for the BRST symmetry. Okay? Let me go on now. Okay, now let's go to the next step. Okay. Now, historical was not done in the way I'm presenting now. Okay, I'm presenting in a modern way. Okay. Now, let me do the following. So we have the gauge field, okay, which is transformed on the gauge transformation in this way. Okay, and I do the following. First of all, I fermionize the gauge parameters. Okay, so this gauge parameter becomes something which is an anti-commuting object. So let me write down first in this way: S of a mu of d mu of c. Okay, so first I replace the gauge parameters. Okay, I replace the gauge parameter by a field. Okay, which is no longer a commuting field, but becomes an anti-commuting field. Okay, this field is known as a ghost. Well, it is known as a Faddeev-Popov ghost, indeed. and actually were introduced simultaneously by Faddeev-Popov and Phiman for electrodynamics. Okay. Then the second thing, I replace this variation here with this symbol S. Okay. This symbol S, it is known in mathematics as an anti-derivation. Okay. So this is just a derivation, but it anti-commutes with fermionic fields. Okay. So this means every time I find a fermionic field, it gives you a minus signs. Going over a fermionic field to give you a minus sign. Okay. So this is very similar to the differential D in differential geometry. So the exterior derivative, which is just an anti-commuting field with respect to the wedge product. Okay. So you see, I replace the gauge transformations by something which is very similar. Okay, but it's a gauge transformation where the gauge parameter becomes a fermionic quantity. Okay. So this is just the first bit of BRST symmetry. Okay. So this is just the BRST transformation of the gauge fields. Okay. Now, since I introduce a new object C, okay, I want to say, well, what is the BRST transformation on this object, new object? And then I just used the analogy with the differential D, and I required that S square must be equal to 0. Okay, so this is nilpotent operators. Okay, which is in geometry is called also a coboundary operator. A coboundary operator. Okay. A coboundary operators. Okay. Then let's try if I can make it. So let's try if I can find a transformation rule for the C in such a way that is nilpotent. Okay. Let me do it. So I have a mu. So I have S of d mu of C. Now S and the derivative commutes, because this is a commuting operator, this is an anti-commuting one, but they do commute. Okay, so I can rewrite as d mu of S of C. Okay, and then if I want to that this is nilpotent, I must have that is equal to 0. So this means S is equal to 0. Okay, so the Gauss field, okay, the C must be invariant under the BRST symmetry. Okay. Okay, so I have two fields, gauge fields and the Gauss, and they transform in this way: d mu of C and S of C is equal to 0. And now I can immediately check that S square of a mu is equal to 0 and S square of C is equal to 0. Yes? Yes, you can do it, but you can say I can put a constant here. Okay. However, this object must be commuting fields. Okay. So therefore, I can put a constant here, okay, but let's say in these schemes there is no natural way to put a constant, okay. Well, one reason is the following, okay. So this in principle could have a dimension, all right. If I put a constant here, it must have a dimension, okay. So therefore, I destroy the conformal invariance of the theory, okay. This is one reason, okay. However, for example, if you consider not just only pure Maxwell, but for example, you want to couple to scalar fields, for example, and in particular, you want to create Higgs mechanisms, okay? Then you immediately see that SC is not 0, but it goes exactly along the breaking parameter of Higgs symmetry, okay? So indeed, you can do it, okay, in a more general context, adding a constant, and that actually, it somehow implement also the Higgs mechanism through the BRST symmetry. Okay, but let's say in this framework, is not natural here to add the constant. But of course, you have these possibilities. Good. Now, in the case of Abelian case, the Abelian case is rather trivial, okay? Namely, but then we'll see it in the case of non-Abelian, which becomes highly non-trivial at this point, okay? However, let me show you one thing now, okay? Good. So now, as I said before, I want to change the action. I want to change the action, okay, but in a way that is somehow trivial, okay. So somehow I want to change the action in a way that I affect as less as possible the theory, okay? So now, since this operator here is nilpotent, okay, I can always find the solution of this equation. S omega is equal to 0, okay? And this means that this omega is closed, or let's say it is BRST closed. Last week we have seen several of these conditions and how these conditions are important to define physical states. Okay, but of course there is a natural or a very simple or a trivial solution of this equation, which means when S is equal S of something, of lambda. Of course, this is now a natural solution, a very simple solution. It's a trivial solution. Okay, namely when you have something which is closed. Okay, something which is closed. Okay, you can have two solutions. One which is non-trivial, and then you can always add something which is trivial in this way. Of course, if this is a solution, also omega written in this way is a solution of the same equations. Okay, namely, if the object is S closed, now also omega it is S closed. I use the word S because I don't want to confuse with the BRST symmetry that I was in Berkowitz last week. I will show you what is the relation between the BRST charge and the BRST symmetry and the BRST symmetry in quantum field theory. Well, there are small differences, but since Nathan was using mainly on-shell from worldsheet point of view fields, so he always using the fields which are on-shell from a worldsheet or worldline point of view, he's able to use a charge, okay? Since we are not using fields which are on-shell, but because we are really dealing with the action, okay, I will use a BRST symmetry, or let's say the differential operator S, okay? This S, let's say this symbol actually was introduced by BRST people because on honor of, actually this was named after Slavnov and not S. Okay, there is an S in the BRS, which means Raymond Storat, okay, but this S is not for Storat, it's for Slavnov, okay. So I use this notation because actually I learned from them that, well, this is, okay. So I use the S notation to distinguish between the Q BRST used last week by Berkowitz, okay. Then I will show you what is the relation by the two, okay. So essentially, the trivial part is something that I can always add to the theory, okay, which looks like a kind of a trivial things, okay. So therefore, if I want to modify my action, okay, this is just a Maxwell action, and then I will do it in this way. I modify the action by something which is trivial, okay. Let me put it omega, like this way. Now, let's first check this. Let me call it this gauge fixed action, okay? I have to tell you what is omega to really to see what is the gauge fixing. But suppose that I define a gauge fixed action in this way, okay? Let's say I add to the Maxwell action something which is trivial, something which is BRST trivial in this way, okay? Now, of course, now, you immediately see the following. If I calculated the BRST symmetry, the BRST variation of the gauge fixed action, I have two terms. I have S of the Maxwell plus S square of omega. Now, because of the nilpotency of the BRST variation, this is automatically 0. Okay, so I don't care what I put here. Okay, I don't care which kind of expression I use for this omega. Okay, it doesn't matter because the action will be invariant for any choice of this omega here, but then you need also the variation of this. However, you see immediately that since the Maxwell action was invariant on the gauge symmetry, okay, and here the gauge symmetry I replaced by the BRST symmetry, so the BRST symmetry for the gauge field, which is exactly like the gauge symmetry, okay, and this quantity is also 0, is also gauge invariant. So let's say the original part of the action, it is gauge invariance, and so therefore it is also BRST invariant, but I added to the theorist something which is a BRST trivial, which is by construction is also BRST invariant. Okay. Good. Now, actually, I want to do it. Now, let me build something here which does what I want, okay? Which does what I want. Okay, to do that, I need to introduce another sector fields. Those are called non-minimal sector. Okay, non-minimal sector of the theory, okay, which must have two properties, okay. First of all, I need something, okay, to construct an action for these Gauss fields. So this looks like a fermion. It is a fermion. It's anti-commuting quantities. So just mimicking what happened for a Dirac action, for example, I need somehow a conjugate of fields, okay. Let me write down this in this way, C bar. This bar has nothing to do with really a Hermitian conjugate or really a conjugate for the fields C, okay? Is another Grassmann or anti-commuting fields, okay, which has nothing to do with the C, okay? Nothing, okay, for the moment, okay? First. The second thing is that, look, if I introduce something, okay, and this something, it is not related to, by BRST symmetry to something else, it might happen that this object could create new quantities which are gauge invariant, or let's say I can create something which could affect my physical space. So I want to add something, but in the meanwhile I want to add another fields in such a way that these two objects somehow conspire to give something which is non-physical, or everything which is created by these fields turns out to be non-physical. Okay, yes? Yeah. In fact, see, here there are no spinors at all. What I'm talking about are fermions. So there's anti-commuting fields. That's it. I don't have any fermions. And indeed, actually, since they are not spinors, okay. So the statistics it's opposite of a scalar fields. So this means the theorem of spin statistics, what also Nathan Berkowitz was saying, in this case is violated because it is scalar fields with the anti-commuting statistics, which means that the spin statistic for them is wrong. Okay, that means that when you look at the Hilbert space generated by those fields, the norm of this Hilbert space has a wrong signature. And this wrong signature, it is exactly what you need to cancel the wrong signature coming from the gauge sector. So the two wrong signatures in the Hilbert space coming from the Gauss sector and from the unphysical sector of the gauge fields, they conspire to cancel each other. And that's exactly the ingredient that you need to have a Lorentz invariant, gauge invariant quantities. No, what is the question? I mean, if there is no spinor indices, I mean, it could be. No, it will not satisfy a Dirac equation. I just want to say is that it is like in a Dirac, for Dirac field, when you have a psi, you also introduce the psi bar. That's it, okay? But the equation for those fields is not a Dirac equations, okay? Okay, so let me first introduce this object, okay, just by what I'm saying is just to build up an action for these fields, okay. But on the meanwhile, I want to add some things, okay, in such a way that the Hilbert space created by those fields are in somehow, let's say, is useful, but in some sense they do not must affect the physical theory. Okay, so let me add here another fields rho. Okay, and now here is a commuting fields rho. Okay, this has a name in the literature. It's called a Nakanishi Lautrup fields. Okay, or Lagrange multiplier. Yeah, I mean, it is a Lagrange multiplier, okay, but has this name because it was introduced in gauge theories by those guys, okay? And these fields C bar and C are known as the Faddeev-Popov Gauss, both of them, okay? Both of them. Okay, also for them, I need to specify what is the BRST symmetry for these two fields, okay? And I will do it in this way. Remember that I want to have this S square is equal to 0. This is just my requirement, my important requirement. And so therefore, I do the following. Okay, I add in this way. S of C bar is equal to rho, and S of rho, let me write down, S of rho is equal to 0. Then you immediately see that S square of C bar is equal S of rho, and this is equal to 0. And of course, S square of rho is equal to 0. Okay, so you see that all the conditions for being nilpotent are satisfied. I introduce two fields, which is C bar and rho, and they are related in this way. Okay, this quantity here, let's say this setup, namely I have two fields and they are related by BRST symmetry in this way, is called a topological quartet. Okay, it's called quartet, besides the fact that there are two fields only, it's called quartet because, okay, in principle, you can add also the conjugate momenta for those fields, okay? So are called quartet, or in the literature you can also find as a BRST doublets. Let's say, this is more in this Hamiltonian approach. They are called topological quartets. In the BRST literature, usually are called as a BRST doublets. Okay, yes? The minima sector I introduce it because now I want to build an action for the Gauss fields. Okay, in order to build the action for the Gauss fields, I need an additional sector. Okay, yes. Yeah, I want to without. Yeah, I want to build. Let's say an action because I want to quantize also the space of the Gauss fields. Okay, so then I need some kinetic terms for the Gauss fields too. No, I cannot derive it from algebraic point of view. At some point, I have to decide what is my kinetic terms for the Gauss fields, okay? And there is no prescription to do it. I can do it in several ways, okay? But the important issue is that the way I built the kinetic terms for the Gauss field has to satisfy certain conditions in such a way that by action, it is somehow independent of the dynamics of those fields, okay? I want to propagate because my physical space, okay, let's say my Hilbert space now, it is constructed out of the quantization of the gauge fields. I choose the gauge fixing, okay. When I choose gauge fixing, I quantize the four components of the gauge fields, okay. So therefore, the Hilbert space for those fields contains both positive and negative norms, okay. So I have this, okay. Now I want to build up another Hilbert space in such a way that the norm coming from this Hilbert space cancel exactly these terms, okay. So this is my ingredient. Exactly. So for each unphysical polarization for the gauge photon, for the gauge bosons, must have an unphysical polarization coming from the ghost. And the fact that those are anti-commutings gives exactly the statistic way to cancel those degrees of freedoms. Okay? But the dynamics, I have to decide what is the dynamics. Okay? Good. So I will do it in the following way. Why actually these are quite important? Actually, last week Nathan built several types of this quartet. For example, at some point he was showing the relation between superparticle in the Green-Schwarz in the Lycon gauge and the superparticle in the covariant gauge. Actually, he added some pieces to the actions, okay, and then he was choosing different representations, okay. But the way he added the theory, these fields actually are really like BRST doublets, okay, so topological doublets. And these doublets, they do not affect the cohomology, they do not affect the physical space. Let's say, if you calculate, for example, the cohomology of just only of this sector, okay, namely you calculate all the operators which are closed under this symmetry, just only this part of the symmetry, but are not exact, you find out that there are there are zero operators which are BRST closed but not exact. So the cohomology of this sector is completely empty. In some sense, you are adding to the theory a physical subspace which is completely empty. It's completely trivial. Okay, this is quite important because actually, for example, topological theories works in this way. Topological quantum field theory, topological strings works always this way. You always find a topological or topological quartet or a BRST doublet which allows to say that your cohomology is empty. Okay. Okay, let's now come to the dynamics. Okay. Okay, let me first do the following. Okay, so now we have the Maxwell action. Okay, and then here you want to add the gauge fixing. Okay, and then you want to add the gauge fixing. Do you remember that actually when I wrote down the Maxwell action, I have two pieces. One was A box A, and the other piece was divergence squared. Okay, I want to cancel the divergence. Okay, if I want to cancel the divergence, the easiest things to do is the following: add the Lagrange multiplier, and then you say d mu a mu. Okay. Now, if you calculate the equation of motion for this action, when I calculate the equation of motion action for respect to rho, I get exactly, so the equation of motion, variation of the action with respect to the rho, is just say d mu, a mu is equal to 0. So just the equation of motion for the Lagrange multiplier. So this is the reason why this rho, it is a truly Lagrange multiplier, okay? You can also view it from let's say path integral point of view. Let me finish it, then I will answer. You can also view this condition as from a path integral point of view. Suppose that you put these terms in the path integral, okay, and then you integrate over these fields, okay. Now, if you have something like this, integral of rho of e to the rho of dA, okay. If you do this integral, okay, well, it's a functional integral, so it has some little problems, okay. But if you do this integral here, essentially, and let me add for the moment just an I, okay. I remove these i's, but you can do it. It's called while trick in order to put back the I in the game. If you put the I here, okay, and you integrate of the rho, it's just a formal derivation, but this produces a delta function of d mu a mu. Okay, so this is just a Dirac delta function d mu a mu. So if you do this analysis from a path integral point of view, integration of this Lagrange multiplier gives you a delta function d mu a mu. So indeed, actually, it forces that the divergence of the gauge field must be equal to 0. Okay, what was your question? Yeah, it's a commuting fields. Okay. You can view also from here. This is anti-commuting, this is anti-derivations, so the anti-variation or anti-commuting fields gives you something which is commuting, okay? Yeah, I will show you, okay? I think that he didn't write this row, okay? But I will show you in a particle in 1 second where this row comes in the game, okay? Yeah, well, the Einbein that was in the particle is the gauge field. And then the condition, actually, he has a condition like E equal -1. The condition that equal to 1 is forced by this Lagrange multiplier. Right, this object here, it is just the Lagrange multiplier I'm introducing here. I will show you in 1 second, okay, how you can get this, okay? Good. Okay, let's say take it this is just only an n-waving way to do it, because just path integral integration, which I don't want to discuss at the moment, okay? But from Lagrangian point of view, it's very clear, okay, that the equation of motion for rho set dA equal to 0. This gauge fixing, by the way, this gauge fixing is called Landau Fermi gauge. Fermi gauge. At the moment here, I didn't put any gauge parameter. You know that when you quantize gauge field, you have a gauge parameter. Actually, also, Gordon Femenov was discussing about this gauge parameter xi. You can set xi equal to 1. Here, at the moment, I didn't put any gauge parameter in the game, okay? Okay. And the Landau Fermi gauge, it is a gauge you can use it, but it's singular gauge. It's not really a good gauge, so you cannot use this gauge for any calculation. But for example, for QCD, it has been used several times. Also, for example, for consider non-perturbative QCD, this gauge, it is good enough. But for other situations, this gauge is not good. For example, if you try to use this gauge in the standard model, where you have like a Higgs sector, for example, this gauge doesn't work. I mean, it works, but gives you singular quantity. So it's better to use a Toff-Veltman Phiman gauge, which contains also the scalar fields. But anyway, these are just a property of the gauge fixing, which is kind of an art to fix the gauge in a correct way. However, okay, so this equation here, let's say this action here, gives you the correct condition, namely dA is equal to 0, and then namely if you add this equation, so if you implement these equations, this action, the Maxwell action, really gives you a mu box a mu. However, this guy here, I wrote down here, it is not of this form. Where I wrote it? Yeah, here. Okay, it's not of the form that I like. Namely, must have like the gauge fixing should be the Maxwell action, which is okay, plus S of something. Okay, but this object is not of this form. But why? Well, we can check immediately. Let's calculate what is S of rho of d mu a mu. Now, when I computed this S, the variation of this, S of rho is give you 0. Okay, fine. But if I go calculate, I get rho of d mu, and then I have this one, which is d mu of C, which is just rho of a box of C, okay? Which is, of course, different from 0, this quantity, okay? It's different from 0. Well, it's different from 0 unless here I add another equations which tell me that the box of C is equal to 0. So I need an additional Lagrange multiplier in order to cancel exactly this term. So let me add here something which is a C bar of a box of C. Okay? Now, if I add these terms, you immediately see that the variation of this is now can cancel exactly that. Because the variation of C bar gives you rho, and then you get so minus rho box of C. Okay, namely, I will do it. Variation of minus C bar box of C gives you, when you calculate the first one, it gives you minus rho box of C, which is exactly what I need to cancel this one. But then I go through, so I calculate S, the S arrives here, acts on C. You get the minus sign because it goes through a C bar, okay? You get the minus sign, but the S of C is give you 0, so there is no additional term, okay? So I was able to write down an action, which is now BRST closed, okay? But the second step is to show that it's also BRST exact. But first of all, it is BRST closed. So you see that these new fields here somehow has the same role of this fields rho here, because this is the Lagrange multiplier for these conditions, and C bar is just the Lagrange multiplier of the other equations. Okay, so I built the kinetic terms of the Gauss C and C bar, okay, accordingly to the gauge fixing that I'm choosing. I choose those gauge fixing, I get these kinetic terms of the Gauss fields. Okay, so exactly because I would like to have a Hilbert space in such a way that the physical and physical degrees of freedom, they do cancel, the longitudinal part of the gauge boson degrees of freedom cancel exactly against the Gauss fields, and therefore the way I fix the gauge gives me the kinetic terms, the dynamics of the Gauss field, which cancel exactly those terms. Let's do the last step. Okay, let's do the last step. The last step means that I want to show that this is a BRST. I want to show that this is a BRST exact. So then I have M plus S of yeah, it is what? It is C bar of d mu a mu. Okay. Let's compute. Okay, let's calculate. So the equation C on C bar gives you a rho of d mu a mu. Okay, then I go through, I get the minus sign because I am going through this C bar, then I have d mu of C. Okay, which is exactly the action that this is just a box of C. Okay, so exactly I got the action that I was tell you before. Okay, so you see that now the result is that the gauge fixed action. Okay, by gauge fixed action, it is indeed BRST. Let's say it is a gauge invariant piece plus a BRST exact piece. Okay, so somehow this object here, from the physical point of view, it's completely armless, so it doesn't change the physics here, but allows you to do the computations. Because now you can write the propagators, you can write down the Hilbert space, you can build the Hilbert space, you can build the propagator, you can compute the correlation function, you can compute the effective action, everything you can compute it. But the way that this is added to the theory, it is indeed somehow unphysical, in the sense that it doesn't change the physics of the model. So do you want to do 5 minutes break, or we keep going? Should we go on? Okay. Okay, let me do it just to reconnect with also Nathan was doing last week. Okay, so what was the situation for the particle? Okay, for the particle we have the Lagrangian, which was like a Pm x dot m plus e over 2p squared. Okay, that's corresponds to my gauge invariant quantity, and S variation of x is just a c of Pm. And then you immediately see, S of Pm is equal to 0. Okay, if you check in the notes that you take last week, you find out that was the variation, the BRST variation, or the diffeomorphism invariance of the theory. You have these two variations here, and then S squared of x gives you S of c of Pm, and this is 0 is f Sc is equal to 0. Okay, then this is automatically 0, but you also have the Einbein here. What is the variation of E? Well, this is just a gauge field, so you get the, I don't remember, I think plus C, and then here there is a C dot. Okay, this is the variation of the Einbein. And of course, you immediately see that S square on E is equal to 0, because S of this gives you this is just derivative with respect to the time, the word line, and it goes through the derivative, and then you get the 0. Okay, then let's do the gauge fixing in this case. I just follow what Nathan did last week. Actually, the gauge fixing that I want to choose the following. So this is the action for the particle plus a gauge fixing S of, then I put a rho of E minus 1. Okay, where actually I have to still to add the non-minimal sector to the theory. The non-minimal sector means S of C, I use the notation that Nathan used. S of B is equal to rho, S of rho is equal to 0. Okay, so this B here, the B here corresponds, I'm write down, corresponds to my C bar. Okay, so the B here corresponds to C bar. Okay, unfortunately in the literature about BRST symmetry for gauge field usually use C bar and C, and in the literature of string theory, particle and superparticle, the anti-ghost usually called B. Okay, but okay, apart of this point here, you see the action now is written in terms of the particle action, which is this one, which is gauge invariant, okay, which is invariant under the gauge symmetry. But of course, since this is invariant, the gauge symmetry is also invariant under the BRST symmetry. Okay, so this action here corresponds to the Maxwell action. Okay, and then I have an exact S piece. Yes, please. Yeah, you're right. That will be B. Okay, good. Thank you. Okay. Right. So you have these terms here which correspond to the gauge fixing. Let's do the calculations. So if I do the calculation, I get the particle action plus, and then here I get rho of E minus 1. Then it goes through, this is an anti-commuting variable, so if you get a minus B, and then from the variation of E, which is a C dot, I get a C dot here. Okay? I get a C dot. Now I can calculate the equation of motion. If I calculate the equation of motion for rho, namely the variation of the action with respect to rho, gives me exactly E minus 1 is equal to 0. Okay? So if I set equal to 0, this is an algebraic equation. Every time I find an algebraic equation, I can always use the resolution of algebraic equation in my action. So I can solve this equation, which means E equal to 1. Then I can use this E, I plug back in the action, and finally I find out, let me write down here. Namely, I find out that the gauge fixed action for the particle, it is what? It is just the particle, which is Pm x dot m plus 1 over half p squared. This is gone because E equal to 1, this is gone. E equal to 1 in this action becomes 1 over 2 half. And then finally the ghost, C dot. Okay, so this was exactly the action that was used by Nathan in last week, actually, which is the gauge fixed actions, okay, with this BRST symmetry, okay. Now, in addition, he has a charge, the BRST charge. Now we'll tell you what is the BRST charge and how you can derive the BRST charge also in this framework, okay. Let's do it in a moment. Okay. Yes, the last things I want to show you for Maxwell, okay, before going to non-abelian theories, is the following. Now we have fixed the gauge. We choose this Landau gauge. We have to find out what is the dynamics of those fields. And then finally, my gauge fixed action, I can write in this way, minus 1/2 of A mu box of A mu, in this way, minus C bar of box of C. Okay, this is just my final action. Of course, it's a free theory. It's a free theory which contains 4 degrees of freedom for the gauge fields and 2 degrees of freedom for the Gauss fields. One way to check that this is indeed reproduced, the correct counting of degrees of freedoms, I can count in this way. These are 4 bosonic, then I count plus 4, okay? And this morning in Terashima was put in infinite, multiplying 4, which means every degree of freedom is a field which has an infinite towers of modes, okay? I'm just counting 4 as this infinite tower of modes for each component of the gauge field, minus 2, which are exactly the 2 fields, because there are 2 Gauss fields, C and C bar, and this gives you 2 degrees of freedoms. Okay, this counting of degrees of freedom, which is just the 2 degrees of freedoms of the polarization of the photon, which matches. For example, you can do the same game, for example, for a p-form in 4 dimensions or in dimensions, and every time you find the correct set of Gauss, okay, then automatically you get the matching of degrees of freedoms, okay. Next time I will show you, for example, what happened for an action for 2 forms, for example, in 2 dimensions, and what is the correct countings of degrees of freedom using this technique for a 2 form in 2 dimensions. Yes? Moral, yes. Yes? Right. We then fix the gauge. No. Afterwards. Right. Then we fix the gauge. Yes. Why this does not fix the BRST? Why doesn't? No. The BRST is a fixed once for all. Okay. So just for the gauge fields, let's say for the original fields, the BRST symmetry is nothing else the gauge symmetry where you place the gauge parameter with the Gauss fields. That's the first sector. Okay. Then you add the non-minimal fields, the non-minimal fields are related by BRST symmetry in the trivial way. That's your symmetry. Okay. And then the gauge fixing is something that you decide a posteriori. Namely, you decide that your gauge fixed action is defined in this way. And then you have another choice. You can choose what is omega here, as you wish, as you like. It depends on what you want to do, okay? If you want to do renormalization group, if you want to do QCD calculations, if you want to do standard model calculations, any kind of theory, you can choose a gauge, a specific gauge. And all these frameworks allows you to use any gauge, but the BRST symmetry is given once for all. Sometimes in the books, what happens is the people don't introduce this row. Okay, let me show you why. Okay, let me show you why. Yes, let me do that because maybe it makes the things more precise. Suppose that I don't want to use this Landau gauge. I don't like it. Okay, but I want to use another gauge, which is for some calculation, it's a little bit more reliable, which is called Phiman Gauge. Okay, the Phiman Gauge is what? Well, usually you see in the book, you add to the theory something which is just minus 1/2 of dA square, something like that. Okay, okay. How can I do that? Okay, I can do it in the following. Okay, let's suppose now to choose omega in this way: C bar dA mu plus 1/2 rho, okay? You see, this object is commuting. This object is commuting. I can do that one. Even more, let me do it in this way. I can put xi here, okay? I put a parameter now here. Here I didn't put any parameter, but now I put the parameter xi in front, okay? Let's do the calculation. Now you have a S of omega. This gives you rho of d mu a mu plus xi/2 rho here, and then I go through, so I get a minus C bar. This gives you nothing, and this gives you d mu of C. Okay? Let's now compute the equation motion. Okay, of course, the gauge fixed action will be the Maxwell action plus this gauge fixing. Okay, if I calculate the equation motion with respect to rho, okay, now with respect to rho, I get d mu a mu, and then I get another piece, which is just a psi rho is equal to 0. Okay? So I just modify a little bit my gauge fixing. So good. Okay. Now you see, here there is again an algebraic equations. Namely, you see, I can solve rho in terms of dA. If I solve it, I find rho is equal to minus 1 of xi of dA. Okay. Let me put now in the action, and I find that the final action, the gauge fixed action, is what? Is a Maxwell. Okay. And then if I do the calculation, so I get a rho here. There is this factor half here. If you do calculation, you get a minus half xi of dA square plus the Gauss field d square c. Okay. So this is the usual gauge fixing that you usually add to the Maxwell theory, okay? Where here, this is just the gauge parameter. In fact, last week, Gordon Semenoff was writing like 1 minus 1 over xi, which is just a way to write down the gauge fixing. Of course, I can choose the gauge fixing as I wish. For example, I can choose xi is equal to 1, and xi is equal to 1 cancel exactly the divergent part of the Maxwell, reproducing the usual Phiman propagator here. Namely, in the case of this gauge fixing, which is called now a Phiman gauge, okay, Phiman gauge, this Phiman gauge actually allows you to remove the rho, okay, to do the calculations and to get done this action. But once you have done that, you find out the following: the BRST variation of C bar, which was a rho, but if you plug this equation here, you get this is minus 1 of xi of dA. Okay, so in some sense here it is a little bit. So it is not longer nilpotent. Okay, this is no longer nilpotent because if you do S square, this becomes proportional to the equation motion of the Gauss. Okay, and then you need the Gauss field C bar in order to have a nilpotent BRST. Okay, in this it's a little bit tricky in this way, but you can either work with all these fields rho, C, and C bar. Okay, or you can eliminate rho in this level. Namely, the choice of gauge fixing is my choice. Okay, it doesn't depend on the BRST symmetry. I don't know if I'm clear.
Maybe you can just add something more on top of what I was asking.
Yeah.
But C is still a gauge parameter.
Yes. Is exactly.
What am I fixing when I write LGF? Am I fixing omega, right? So I'm not fixing the gauge, I'm fixing kind of the BRST.
No. But the end of the day, this action here, it is no longer invariant under the gauge symmetry. It is invariant under the BRST symmetry, but it's no longer invariant under the gauge symmetry. In fact, this action here, it is not. Well, this part is still the gauge invariant, but this object is not no longer gauge invariant. So this breaks the gauge invariance, independent of the parameter. Of course, you can choose the parameter as you wish, but this breaks the gauge symmetry anyway. Okay, it is BRST invariant, but it's not gauge invariant. Okay, so this is the reason why now you define your Hilbert space, you define your path integral, everything in this case, but you still have the BRST symmetry, but no longer the gauge symmetry. Okay. Good. Yeah, the last things I want to say, also, let's say, to make it more precise in this case. So you can do path integral in this case. Now, these are free fields. You can do path integral. Now, the path integral of these bosonic fields gives you one over the box to the fourth in the denominator. And this is just a commuting parameter. So when you do path integral on two anti-commuting parameters, it gives you something on the numerators. Okay, gives you box square. So box square over. Okay, box square over, and then both to the 4 down. Okay, and this cancel gives you 2, and this is just 1 over box square, which is the correct propagator for the photon. Okay, so namely the cancellation of degrees of freedom, you can view it also in this way. Of course, you need to regularize the zero mode and blah blah blah, but okay, this is another issues. Okay, because of this. I'm sorry. It is like this. Okay. Yes. Okay. Yeah. Half of them. Yes. Yeah. Yeah. Sure. Okay. Thank you. Okay. Okay. Now, actually, we are in the position to do. Non-Abelian gauge series. Okay, so now here I just translate what I did for Maxwell, okay, in terms of non-Abelian gauge fields, because I want to add also interactions and to see how this works also in this more general setup. Okay, so if I add the gauge fields, okay, now this object can be viewed as a matrix valued operator. So I had here TA, what are the generator of SUN group. I just stick to SUN. I don't need to do, let's say, stranger things. So let's do SUN, and they satisfy the following commutation relations, which is I of A, B, C, T, C, where, so these are Hermitian operators, Hermitian generators, and these are the structure constant of SUN, okay? And these are the commutation relation between those generators, okay? Now you have to add, somehow to update a little bit your dictionary. For example, the field strength, okay? Let me write down the field strength in this way. d mu a nu minus d mu a mu plus I over g, ig times a mu a nu. Where this commutator I wrote down here is just the Lie algebra commutators of SUN, okay? And indeed, actually, if I substitute to this definition, you find out a mu is equal to what? A mu TA, A mu B TB. That gives you A mu A mu B, and then I have TA TB, TB, and this gives you I over G F A B C A mu A nu B TC. Okay. So the non-linear terms in the field strength has 1 power of the field strength of the structure constant I over G, which is just the coupling constant. Okay, so you saw this already in the lectures of last week by Gordon Semenoff. Okay. Yeah, a few things. One thing that you have to remember is just now how the gauge transformation goes. Okay, so the gauge transformation of the gauge field now is just d mu lambda. So I put here the gauge covariant derivative. The gauge covariant derivative is just d mu of lambda plus I times g of a mu lambda. And also this object is has a value in the Lie algebra, so TA, okay. So therefore I can make it more explicit. If I do that, I find out that the gauge variation of the component A is just d mu of lambda A, yes, g of A, let's say B, C, A B mu lambda C. Okay. Written in terms of, yeah, it's pure real expressions. And okay. Now, by a little bit of algebra, you can check, you can check that if you take two variation with the parameter lambda 1 of a gauge field A mu, d mu of lambda 1, and another one, 2 of a mu as d mu of lambda 2, then you find out that if you calculate the commutation relation between these two transformations acting in a mu, then you get the variation of the gauge field, again a variation of the gauge field, where the parameter here of this transformation is just d mu of commutator of lambda 1, lambda 2. It might be probably a IG in front. Okay, so the gauge parameter here, there is IG. Okay, in order to respect all the properties. Okay, so namely, so this is the non-Abelian nature. Okay, the gauge transformation of these two gauge transformation give you again a gauge transformation of this type. Okay. Now, if you calculate what is the gauge variation of the field strength, which is also has an index, so it has a value in the Lie algebra, if you do the calculation, you find out that this is equal to I over G of F mu nu times lambda, where this again is the Lie algebra bracket for the for these fields. So I'm going fast here because I suppose that you know these things very well. Okay, it depends on the let's say on the notation, but more or less you find the same result. Okay. Now the Lagrangian here in this case, this is Yaming's Lagrange. It is minus 1 over 2 trace of f mu nu. Okay, so instead of writing this way, I want to write for the component fields. I get minus 1 over quarter f mu nu a, f mu nu a, where I raise and lower the indices using the Killing-Cartan metric for SUN, namely trace of TA TB is equal to 1 over half eta AB. This is the Killing-Cartan metric for SUN, which is definitely positive. Okay? Well, now you know that this action here it is gauge invariant, okay. And of course, if you calculate now the let's say the component, let's say if you write down in terms of the potential, this expression has of course the same kinetic terms, the same quadratic terms as in the Maxwell theory, but of course you get interactions. Okay, so you get the quadratic pieces, which is exactly the same as in Maxwell, but then you get the two interacting pieces. One interaction which is a 3-point functions, namely a vertex with the 3 gauge bosons, and there is another interaction terms which is just the 4 boson interaction. Of course, this depends on one derivative, and this does depends on any derivative. So these are the two interaction terms that you find down in this Yang-Mills action. Now, so the theory is fully interacting, is non-trivial, so we know everything about this theory. Now, what happened to the BRST symmetry now? Let's go to the BRST symmetry. No, well, before doing BRST symmetry, let me do it something still on the gauge invariant side before doing BRST symmetry, okay? And then I want to say something about the word identity again, okay? So what I did for the Maxwell is deriving the word identities. Let me do it also for non-Abelian case. So I'll do the same game. So I do the variation of the effective action, which I write down exactly in the same way, d for x, variation of d mu, okay, and then the variation of the action with respect to a mu. However, you have to remember that these objects are in the Lie algebra, okay? So I can do it in this way. Either I write down in terms of the component, or again I write down using a trace, okay? Let's say I have to put a trace here, and I have to remember that any variation of gamma with something which is a Lie algebra value object, you have to do it carefully. So essentially, you have to do it, let's say, component by component. So let's say in order to make the things easier, I write down in this way. So I take component by component, and then I already take the trace. I use the trace for these matrices here. So you can check that the variation of this object with respect to one connection with Lie algebra value can be written as proportional to Lie algebra generators. But okay, but this is an easier way to do it. Now if I stick here the gauge transformation, then I get d for x. Then I have a covariant derivative of lambda. Okay, of course this is an index a of d gamma of dA mu a. In this way. Now I want to do a partial integration. Okay. Of course, for the derivative there is no problem. I can do partial integrations, okay? But then there is also a part which contains the gauge fields. Namely, this object has two pieces, d of lambda a minus g of f b c a mu b lambda c, okay? So this one, if I do partial integration, I get a minus sign. Okay, but also this one I get a minus sign because I'm not doing partial integration, but what I'm doing is I'm exchanging these two indices. Okay, the indices on the structure constant in the case of SUN are fully antisymmetric. Okay, so therefore just exchange these two indices. Okay, I get another minus sign. So this means I can take this covariant derivative and I can replace this covariant derivative and I plug it here. So by integration by parts, so this is just non-Abelian integration by parts, I get a minus lambda of a of covariant derivative of d of gamma of a mu. Of course, this has an index because this is a covariant derivative acting on something which has an index in the vector, in let's say in the adjoint representations. Okay, and then I write down in this way. Of course, this must be equal to 0 for any gauge parameters, and therefore the word identity I can finally write down as minus d mu of d gamma of dA mu is equal to 0. Do you remember, in the case of Maxwell, okay, let me write down this explicitly. I have d mu of d gamma of a mu, and those are the Maxwell part of the word identities. But then I have another pieces which is plus g. Now, of course, I will make mistakes of indices, but anyway, you can check it by yourself. Okay, so you see that there is the Maxwell part, is this one, but there is an object which is just the non-Maxwell part. Okay, of course this is non-linear in the sense that this is just a differential operator d, but here it contains even the fields. Okay, now this is essential because let's say the gauge field itself it is charged under the Yang-Mills symmetry, and therefore you get this term. So if you add also Maxwell or other fields, if you add, for example, matter fields, they will appear in these word identities. Now, if I do the game that I did for Maxwell, for example, for tuple functions, if I consider tuple functions, which means the following. So if I consider tuple function mu nu a b, x and y, which is just the variation of a mu a of x, a nu b of y, computed for a is equal to 0, so this is the tuple functions. And then if I use these equations in the word identity, I have to do the following. I have to take one derivative of this expression, of this functional equation, and then I put a equal to 0. Okay. Now, of course, here I get the tuple function because I get another derivative here. Okay. Now here I have two situations. Either the derivative acts on this, okay, and then when I put a equal to 0, give you just 1 point functions, okay, or the derivative acts here, okay. But when you put a equal to 0, this drops out, okay. Now, there's still one-point function. However, the one-point function in the case of Yang-Mills, without any Lorentz breaking everything, it vanishes by Lorentz invariance. Okay, so therefore there is no one-point function. So therefore, the word identity for two-point function, it is equal exactly the same. Nu b x and y is equal to 0. It's just the same word identity for two-point function for the Maxwell theory. Okay, if you just translate into momentum space, this becomes I of p mu of gamma mu nu a b, and p is equal to 0. Okay, so this means, so if I consider two-point function, so I have two-point functions. Here I contain all possible radiative corrections. So as a mu, a and b, and there is a momentum p propagating inside of this. If I contract this function with the pi mu, that gives you 0. So this means that the two-point function must be transverse according to these equations. What happens if I do for three-point functions? If I want to do it for three-point function, I have to take an additional derivatives, an additional functional derivatives. So this means here I get two derivatives, I get the three-point functions, but here I get other two derivatives. One derivative could act on this, another derivative acts on this. Or the two derivatives can act on this. If three derivatives acts on this and you put a equal to 0, this drops out. But if one derivative acts on this and one derivative acts on this, gives you something. Okay. So therefore, for three-point function, I have another equation which is like this. I write down immediately in the momentum space I plus q mu gamma mu nu rho a, B, C of x, on P and Q, okay? I use the momentum conservation to say that the momentum on which this three-point function depends are only two of them. And then I have pieces like plus G, and then I have F. Now here, let me write down, okay, B, D, gamma, B, C, nu rho, plus G of A, D, C, gamma, sorry, it was D here, okay, and B, D of nu rho. This is a function of P, and this is a function of Q, is equal to 0. Besides some minus sign or some small correction, you see now that the three-point functions, now this is three-point function, so let me represent it as a three-point functions in this way. So this is a mu A, mu B, rho C. These are three lines, and this is momentum P, and this is momentum Q. So it flows here the momentum P plus Q in these lines. If you contract these lines with P plus Q, okay, you find out that the contraction with the P plus Q mu of this three-point function gives you a two-point function, one-point function here, minus, and so this must be minus, I guess. Another point function here. Okay, this is a point function with P, and this is a point function with Q, with the F in front, like this. Okay, so this tells you that the three-point functions, it is related to two-point functions here. You can check that along these lines, for example, is transverse. Along this line is transverse, and because these two guys are transverse along these lines. Now, in the next lectures, Luca Griguolo about anomalies will show you an application of these equations. Okay, so here we have an identity. Let me point out a point here, which is very important. Okay, you see that here in this identity it appears just one fields. Okay, these guys contain one fields. Okay, this is essentially because every time I take a derivative, a functional derivative, either the functional derivative could act here or could act here. Okay, but suppose that instead of a fields here, I have a double fields. For example, suppose that here I got a product of two fields that I'm going to have it when I consider BRST symmetry. It happens that I have to take into account additional diagrams, and this is the reason why you need antifields. Okay, so today I will not have time to do it, but I will show you now next lectures why, for example, if I'm going to write down the word identity for the BRST symmetry, I need antifields. And then the antifields belongs to a nice geometrical setup called Batten-Wilkowski framework, which was discussed by Berkowitz last week. Okay, so it is important, these word identities, because this gives you somehow other geometrical structure that I will add to the theory. Okay, that's clear. You find also in these books, for example, in the Zuber books, you find these equations, but you find more or less all textbooks, these word entities. So, the last 10 minutes, I will introduce the BRST symmetry for Yang-Mills, and next time I will go on and build the quantization for super Yang-Mills. Okay, let me do next step. Now we have now we follow the same steps as before. Okay, so we have the gauge transformation A mu A, which is just d mu of lambda A, or if I want to write down completely, it's just a minus G F B C A mu B CA, sorry, lambda C, okay? And then first I do fermionizations, okay? So I fermionize this, and fermionize, I write down S of A mu A as a covariant derivative of C. So I just promote the gauge parameter to a Gauss field, okay? It becomes a Gauss field, namely it becomes an anti-commuting quantities, okay, which again has an index in the same adjoint representation. Of course, you can do the same calculation using, instead of using the component, you can use matrices. Okay, so S of A mu is just the covariant derivative of C, which can be written as d mu of C plus I of G of A mu times C. So if you can do it with bracket, okay, in this way. Let me mention just one small thing. I'm not going to do with the geometric counterpart of this, but A mu, indeed, actually, it is just a component of a geometrical quantity which is called a connection. Okay, namely, a connection. It is one form which has exactly those components. Okay, in this way. So if I write them as a one form, okay, I can rewrite this equation in this way: S of A is equal of d of C, so this is the usual differential, plus I of G of A times C. Okay, you see here I suppress all the indices. I suppress the Lorentz index, I suppress the Lie algebra index, and this is purely geometrical quantities. But if you like, but probably Terashima will also use this notation. I don't know, but you will find in books and in several papers. I mean, this is a starting point to understand the BRST symmetry from more geometrical point of view, namely just an interplay between the BRST symmetry and the differential geometry. It emerges from these equations. I'm not going to say more than this. If you like, you can ask me. Yes? Yes, it is some flatness, yes. Okay, let me add something now, because, okay, yeah, so what you can do actually, you can promote the gauge field to add the gauge field plus the Gauss field. So you see, this is one form, okay? So in respect to the wedge product, this is an anti-commuting quantities, okay? So, and then you add the C. Somehow you're promoting your gauge connection to have like a fermionic leg in your cotangent bundle, okay? And then the BRST operator, let's say the differential D, get an additional pieces with just the BRST symmetry. So you add this. You're generating what is known as a double complex, okay? And double complex, I mean a double complex with two differential. One is differential, which is the differential on the base manifold, and S is just the differential along the fiber, okay, in this way. So essentially C is just the component along the fiber. Okay, you find in the literature the full discussion of this. And then you find out that since the object must be nilpotent, also the combination of those must be nilpotent. So this is nilpotent, S must be nilpotent, and they must anti-commute, because these are anti-commuting differentials, okay? So they must anti-commute. And then if you require that the D plus S acting on the A plus F is equal to 0 or is equal to gauge connection, then you get the flatness conditions from these equations, yes. So the flatness condition gives you the full BRST symmetry. The formula is known in the literature as a Russian formula, where actually this was built. If you like, I can give you the references for this. Yes, I don't know by heart. I will give you the reference next time. Okay. Okay. Yeah. Right. So now we are at this point. Okay. So now the next point is the following. Okay. Look. Now I set up with this just the BRST symmetry, which is nothing else than my gauge symmetry where I fermionize. So I know that at least the Maxwell, the Young-Mills part of the action, it is invariant under such a symmetry. Okay, this guy depends only on the gauge fields, depends on the field strength which was formed correctly, and therefore this is BRST invariant. So being the gauge invariant, it is also BRST invariant. Now, however, I want to set up the stage in such a way that this operator here must be nilpotent. So S square of A mu must be 0, okay? But now actually it is a little more complicated because now this guy, it depends on gauge field itself, okay? So let me do the calculation, okay? So whatever, S acting on what? D mu of CA plus G of A, B, C, A mu, B, C, C, okay? Now if we do the calculation, this part is just the D mu of S of C, A, fine, just leave it like this, okay? But now here I have two pieces. One is S acting on A, so I get G, F, B, C, A. Then I have to take this one, which is just D mu of C, B, plus G, F, so let me see, D, E, B, A, D. Sorry, I'm at the end of the blackboard, but hope that you read it. CC in this way, okay? And then additionally, I still have to act on C. So finally, I will going to write down on the blackboard in 1 second on the other side. BCA, A mu B, S of C. Okay. Now this piece here, this part here, and this part here are going to be together. Right, and then I can rewrite this in this way. I have a covariant derivative of S of C, A, and then here I have still these two pieces here, okay, these two pieces here, but then you find out the following. You see, these terms, it is just G of FBC, D mu C, and CC, okay. So it's a plus G, F, B, C, A, D mu of CB, CC. This one piece, okay? And then there is another piece, which is these guys with gauge fields, okay? Which is just G square, F, and then I have two pieces, which is BC, A, F. Now, here there is, let's say, what is the next term? Okay, so here was the B, so F, D, E, B, A mu, D. So there is a, yes, C of C coming from here, a C of E coming from here. Let's see, okay. There's a C of E and C is C, okay. So no, the order is wrong. Yeah, E and C, like this, okay. Okay, now here it happens the following. First of all, this is antisymmetric quantities, okay. So being antisymmetric means these two indices here must be antisymmetrized correctly, okay. Yeah, here I did it in a different way, okay. And then, okay, and then you can recast everything, okay. So also here you see the following. So here there is D mu of CB and CC, okay. Now since there's B and C so this is antisymmetric in these indices, okay? So this, you can symmetrize and antisymmetrize this object, okay? And also this happens here. Okay, if you put everything together, you find out that this gives you d mu, and then you get C of CA plus 1 over 2 F BCA CBCC. So here I did the two things. I did this antisymmetrization, I show you. And the second thing is I rename the ghost in such a way that this appears with this name, okay? So the index A is the open index appearing in the variation of the gauge potential, and the indices FB appear here, okay? So you can check it that you can rewrite in this way. Finally, then I want to make it this is equal to 0. Okay, so then I find out that the C of a CA is equal to minus half. So I forgot that there is a G here. Okay, G of ABC CBCC. So this is the famous transformations, the nonlinear transformation for the ghost field. Do you remember that last week Nathan Berkowitz was discussing, for example, superstrings? Okay, so he was considering the supersymmetry generators, and the supersymmetry generators were satisfying some algebra GB is equal to some operator PAB. I don't remember now. Well, it was like some gamma AB. So this was like alpha beta gamma alpha beta APA, okay? So it was saying that the supersymmetry algebra is non-linear, it's non-Abelian, okay? And therefore, the transformation of the ghost or the BRST symmetry has somehow the terms with the two ghosts and one anti-ghost, okay? And here I recover in a different way, namely the nilpotency of the BRST symmetry required that the BRST variation of the ghost, now it is proportional to a product of the ghost. Now let's check if everything is correct. First of all, the indices are, well, here, okay? So that was not correct. So the index here is matching correctly. These indices BC are contracted with the index of the CB of the ghost field. And those are antisymmetric, and these indices are antisymmetric, which is fine. The dimensions works because, well, you can fix as this dimension 1, it gives you dimension 2, is okay. So it depends on the coupling constant, okay, and depends on the structure constant. Therefore, if the structure constant is 0, like in the Maxwell theory, that of course gives you 0, which is exactly matches what you've done so far with the Maxwell theory. Okay. The last things that we want to check is S square of C of A is equal to 0, okay. Now, how this works? Well, if I do S square, okay, it happens that S acts here, but also acts here, okay? But then, what happens is that every time I make a BRST transformation of a ghost, I produce two ghosts, okay? So then at the end, when I do the calculation, I get the 3 ghosts in this case, okay? But 3 ghosts must be totally antisymmetric in these indices, okay? So you antisymmetrize. So let's do it. So I get minus half. So I'm doing S square, which is just minus half of G squared. Then I have FBCA. So I did this one, which is F. Then I have, let's say, a DEBCDCE, CC, okay? And then I have another piece, which is minus CB, and then I have FDECCDCE, okay? Now I have to do a little bit of renaming, okay? And then I have to fully antisymmetrize in these indices, C, D, E, C. If I do that, okay, you find out that the full antisymmetrization appears on the indices of the structure constant, of 2 structure constant, and this is equal to 0 by Jacoby identities. The Jacoby identities, which are essential to have really a Lie algebra, okay, the Jacobi identity is a consequence of the fact that you're working with the Lie algebra, okay, implies that the BRST symmetry on the ghost field, it is indeed nilpotent. Indeed, actually, you can somehow implement the full Lie algebra in terms of the ghost. It's called ghostifications of the Lie algebra. Namely, you represent it using fermionic variables, and the fact that the BRST operator it is nilpotent, it is equivalent to require that this is Lie algebra with the correct Jacobi identities. Okay, I think I am stop here. So next times I will introduce the no-minima sector, okay, and then I will show how to do gauge fixing, and I will show this, the word identities and how to quantize the system, the symmetry. Thank you very much.